So, good morning, everybody. Welcome again for this new seminar at the Severo Ochoa Colloquium. And today we will have the talk by Victor Mauricio Gomez Gonzalez. He's from the Institute of Physics and Astronomy in Potsdam, in Germany. And he will talk about studying star formation in collisional galaxies with MUSE. So Mauricio will be properly introduced by Isabel.
Hello, good morning, everybody. Thank you very much for being here again for a new colloquium from Severo Ochoa program at the IAA. So thanks to all the people here in the physically present in the Salon de Actos and also online. And first of all, thank you very much, Dr. Victor Mauricio Gomez Gonzalez, to have accepted our invitation. It's a pleasure to have you here among us. Our today's speaker, Dr. Mauricio Gomez Gonzalez, as René said, serves as a postdoctoral researcher at the Institute of Physics and Astronomy in Potsdam, in Germany, a position he has held since 2021, with plans extending to 2024. He obtained his PhD in physics, in astrophysics, in 2017 in the Instituto Nacional de Astrofísica, Óptica y Electrónica in Puebla, in Mexico. Then from 28 to 29, he held his first postdoctoral position at the Facultad de Ciencia en Física y Matemática, Universidad Autónoma de Chiapas. I adore saying things in Spanish. Then he worked at the Instituto de Radioastronomía y Astrofísica in the Universidad Nacional Autónoma de México until 2021. His research in astrophysics covers various topics, including Wolf-Rayet phenomena, massive stars, H2 regions, extragalactic star formation, and planetary nebulae. Today, as you know, the talk would be about studying star formation in collisional galaxies with MUSE. MUSE, as you know, is an integral field spectrometer. MUSE datacubes offer the opportunity to study the ionization mechanisms and the chemical abundances in stellar clusters complexes hosted in the H2 regions. IFS, or integral field spectroscopy data, also offers an opportunity to unveil the presence of population of Wolf-Rayet stars and the sources of ionization potential emission lines like helium-4686 in the nearby universe. So thanks again, Dr. Mauricio Gomez Gonzalez. The floor is yours.
Thank you. Hi, everyone. Good afternoon. First of all, I would like to thank especially to Martin Guerrero, also to Carolina Kerik and Pepe Riches for the invitation to this wonderful institute, and also for the opportunity to talk about my work. So the title of my presentation is Studying Star Formation in Collisional Galaxies with MUSE. However, in order to be more specific, when I say star formation, I'm mainly interested in the most massive stars and in the Wolf-Rayet phenomena. And when we say collisional galaxies, these systems can be in a pre-collisional stage during the interaction or in the post-collisional phase. So we have been working mostly with MUSE for extragalactic objects, but also with Megara in the GTC with other collaborators. So I would like to mention some of my main collaborators in Mexico, Diva Caramaya in his group, Javier Zaragoza from INAOE, also Jesus Tuala, Jen Arthur, and Gustavo Brusual in their group in Iria, Gerardo Ramos in his group in Guadalajara, Martin Guerrero here in Spain, and hopefully many others in the near future, and also the Power Group in Potsdam, Germany, where I'm currently doing my postdoc. So in this talk, I would like to concentrate in these three systems, these three galaxies at different distances. First of all, M81, which is this grand design spiral galaxy, actually very similar to a Milky Way in mass, morphology, although a little bit less metallic, at a distance of 3.6 megaparsec. Also the antenna, this spectacular two galaxies in a process of a collision at 18.5 megaparsec. And also, our last work has been in this very nice galaxy, AM06444741, which is a double ring post-collisional galaxy at 98.6 megaparsec. So here in these three systems, we have studied the most massive stars and the Wolf-Rayet phenomena. So why massive stars? Why massive stars are interesting to study? Okay, first of all, let's start with the definition. The massive stars are those with initial masses in the main sequence equal or higher than 8 solar masses. And because of these masses, they are of course very hot and also very young, from 1 to 20 mega years. And they are key to understanding nucleosynthesis processes such as the CNO cycle, the triple alpha process, and they have an impact on the interstellar medium feedback because of the mass loss through strong stellar winds. The massive stars are expected to inject mechanical energy, ionizing photons, and new elements in the local environment. And this, of course, has an impact on the evolution of the galaxies. And for cosmologists, these stars are important to understand the reionization of the universe. And also stars are even more massive, with initial masses higher than 20-25 solar masses, but they can be as massive as 50-100 solar masses. These are the O-type stars. They lead to some of the most exotic objects in astrophysics, such as the classical Wolf-Rayet stars with strong stellar winds, also core collapse supernova, when we see. Also, the observational link between these two is missing. I will say later what do I mean by this. Also, the long duration gamma ray bursts, compact objects such as neutron stars and black holes, and lately the gravitational waves. In this Hertzsprung-Russell diagram, I show you evolutionary tracks for massive stars of 10, 20, and 40 solar masses, considering the single and binary channels. And I wanted to show you here where the Wolf-Rayet stars are expected. So they are basically the last stage of the evolution of the O-type stars. And interacting galaxies like these three systems are excellent places to study massive and Wolf-Rayet stars because the star formation is triggered in galactic scales in these interactions. Yeah. So I mentioned that the link between the observational link between classical Wolf-Rayet stars and the core collapse supernova is missing, and for this I will need to make a brief historical parenthesis. So basically, when these two guys, Charles Wolf and Josh Rayet, discovered in Paris the first three stars with emission lines in their spectra, later known as Wolf-Rayet stars, have passed more than 150 years. Yeah? And since their discovery, none of the non-Wolf-Rayet stars have exploded as a supernova. Yeah? And if we consider that the progenitors of the Wolf-Rayet stars, which are O-type stars, have ages of 10 to the 6 years, mega years, and the Wolf-Rayet phase is 10% of the age of the O-type star, 10 to the 5 years. So we will need at least 10 to the 4 stars in order to have at least one supernova in a human lifetime. Yeah? But if we consider that we only know around a bit more than 600 Wolf-Rayet stars in a Milky Way, we will have to go extragalactic, yeah, to have more candidates to observe a supernova. So these are the first 14 Wolf-Rayet stars that we discovered in MRE1 at 3.6 megaparsec. These are HST images. The Wolf-Rayet stars are in the center of the images. As you can see, they are located in very complex star-forming regions. Yeah, they have a nebular gas of sizes of around hundreds of parsec. And this is how the spectrum of a Wolf-Rayet looks like. This is not the best spectrum of a Wolf-Rayet, but it's one of my favorites because it was the first Wolf-Rayet star that we found. So basically, you can see this was taken with Osiris in the GTC. You can see a blue continuum, a lot of emission lines, narrow lines. It's because of the nebula in front of the Wolf-Rayet star. consider that at 3.6 megaparsec, an aperture of 1 arcsecond is 20 parsecs. So there's more than only the star inside the aperture. But these two lines, these broad lines here, are the fingerprint of Wolf-Rayet star. Yeah, only Wolf-Rayet stars can produce these lines. So these are known as the Wolf-Rayet features. This is the blue bomb and this is the red bomb. The blue bomb is made basically by helium-2 at 4686 angstroms, but it can also have nitrogen-3 to nitrogen-5 or carbon-3 to carbon-4. And these are elements, these are products of hydrogen burning through the CNO cycle. And when only this bomb is observed, these are associated with nitrogen-rich Wolf-Rayet stars. On the other hand, when we also observe the red bomb, which is basically the doublet of carbon-4, 5801, 5811, which is a product of helium burning by the when we also observe this bomb, these are related with the carbon-rich Wolf-Rayet star. So in this case, this is a WC star. And so later we found an additional 7 Wolf-Rayet stars in M81. This is their location in M81. So basically they are in the disk, tracing the spiral arms. Here different colors indicate differences of observation. We started with long slit, but then we continue with MUSE in GTC. And in this diagram, I show you the luminosities of the red bomb, carbon-4, versus the luminosity of blue bomb, helium-2. And these are the 21 objects. Here, the color indicates the classification that we made using templates of individual Wolf-Rayet stars in the LMC, because this is the metallicity of this galaxy. And here you can see in blue the location of the nitrogen type late Wolf-Rayet stars. In purple, nitrogen early. Early is a higher stage of ionization. We also found intermediate Wolf-Rayet stars between nitrogen and carbon. And in red, I show you the carbon type Wolf-Rayet stars. We didn't find WO type stars here. Here the green dots are multiple systems dominated by carbon type Wolf-Rayet stars. So interestingly, Peter Conti proposed a Conti scenario where so Wolf-Rayet stars the descendants of O-type stars, right? So when you have an O-type star and before exploding as a supernova, it goes through the Wolf-Rayet phase. Okay, you cannot see here, but it goes through the Wolf-Rayet phase, depending of its mass. It can go through the nitrogen type, transitional type, the carbon type, and this is exactly what we see here in this diagram. Yeah. So actually, the luminosities of individual Wolf-Rayet stars in the LMC are indicated here with these stars. So we propose this diagram to classify Wolf-Rayet stars. If you only measure the red bomb and the blue bomb and put the luminosities here, you have the classification. Of course, there are more sophisticated classification systems, but this is very fast. Let me make a brief parenthesis just to mention that the Wolf-Rayet phenomena is not exclusive for massive stars. Actually, some planetary nebula have central Wolf-Rayet stars, yeah, like this one that I show you here. And these are in the transition between the AGB and the white dwarf stage. You can see here a spectrum of this star AGC 6905. So here you can see the bombs, the blue bomb, helium-24686, carbon-4, and also oxygen-6. Yeah, actually, I've never seen so many broad lines in the spectrum of as in these central stars of planetary nebula. So, but only 21 stars in M81 are not enough to increase the sample of Wolf-Rayet stars that we already know, right? So we have to go to more extreme systems. What a perfect system that the antenna. So this is the nearest pair of colliding galaxies, the AGC 4038 and AGC 4039. They're at a distance of 80.5 megaparsec, and there is a significant number of star-forming regions and H2 regions here, and there are a lot of studies and multiple observations in spectroscopic observations. Here you can see in infrared with Spitzer, Antennae, in Chandra, a combination. Yeah, so these are excellent places to look for Wolf-Rayets. So actually, each object that you see here are not, of course, not stars. You cannot see individual stars at these distances, but not even clusters. These are star-forming regions. Yeah, these are more similar to what we observe in the LMC, like Teridorados, where we have a compact cluster in the center and a more extended cluster of hundreds of parsecs. So in Mexico, at some point, I was teaching some students how to download data from GTC archive and how to reduce with IRAP, etc. And we found serendipitously Wolf-Rayet features in this object, which is in the bridge between these two galaxies. And we were very excited, and we wanted to make a proposal with Megara. However, before submitting the proposal, we also found that it was already observed with MUSE. Yeah, so we didn't submit the proposal. We analyzed the archival MUSE datacubes to look for the Wolf-Rayet stars here, and we were very lucky. We found 38 regions indicated here with the red circles with Wolf-Rayet features. Yeah, here these rectangles indicate regions where Whitmore measure and report extinction of these objects. So this is how the spectrum of MUSE looks like for this object. You can see a lot of narrow nebular lines, and here are the blue bomb and the red bomb. Yeah, these are very weak. Actually, if you're not looking for them, you might miss it. We also find other kind of options, because we were looking for the blue bomb at 4636, and sometimes you find this kind of objects. In this case, this is a quasar. Yeah, so it has also broad lines, but these are Balmer lines at the redshift of 0.2. Yeah. So sometimes you are looking to find those kind of objects, and so this is MUSE, and this is the first spectrum that we found with OSIRIS. So with OSIRIS, the advantage that it has is that it sees a bluer range of the spectrum from 3,600 to 7,200. MUSE is from 4,700, sometimes a little bit bluer, 4,600. Yeah, but sometimes because of the redshift of the galaxy, you can see the blue bomb. So this is very necessary in order to look for a feature for WO type stars, which are oxygen 63811. In this case, we didn't find this feature because indicating that there are no WO type stars in this object, but we could only do this for this object. Actually, maybe it's not such a bad idea to make the proposal with Megara to look for the population of WO type stars. Yeah. So in order for you to believe me that these are features, so this is a zoom of these two Wolf-Rayet features. So here you can see the helium-2, carbon-3, nitrogen-3. There are two approaches in the literature when you have Wolf-Rayet spectra, to use templates or to use multi-Gaussian fittings. We use both for this study, but we also like this approach because you can take into account the nebular lines, yeah, in order to report the widths and the luminosities of these features. But we also use templates of individual Wolf-Rayet stars in the galaxy in order to quantify and to classify the spectra. So we did this for all the sample. So here I will show you some interesting luminosity diagrams. So this is the luminosity of the blue bomb, carbon-4, luminosity of the, of the red bomb, carbon-4, blue bomb, helium-2. And these are the 38 objects in antenna. So consider that the luminosity for only one Wolf-Rayet star is 10 to the 36. Yeah. So here is indicating that there are hundreds in each region, hundreds of Wolf-Rayet stars. So, and this is the luminosity of H beta versus luminosity of blue bomb. So H beta is because of the gas, and blue bomb is only because of the stars. So this is telling you that the higher the number of Wolf-Rayet stars, they have an impact on the feedback of the nebular environment. And these are the equivalent width of H beta versus equivalent width of helium-2. And this is very nice to plot because it is expected that equivalent widths higher than 50 angstroms, those regions are younger than 4 megayears. Yeah, so we found 4,000 Wolf-Rayet stars in the antenna. Yeah, half of the stars are nitrogen type and the other half are carbon type. So we plot the ratio WC over WN versus metallicity. And the models from BPAS, from Eldridge, 2017, propose, these are the models for single populations, for binary populations in blue. And for reference, I plot here the median value for the SMC, the LFC, and the Milky Way. Antenna is here. So this is consistent with single population of all-type stars as progenitors of the Wolf-Rayet stars. It's not so weird because this is high metallicity. Maybe a lower metallicity binary are more common. The binary channel for Wolf-Rayet stars. And this is the Wolf-Rayet over all-type star ratio. Yeah. So this is the value is an upper limit because we consider that we counted all the stars, the Wolf-Rayet stars, but we are not pretty sure that we counted all the all-type stars because it was only a rough estimate because of the luminosity of H beta. So, but only finding this number 0.1 is also very nice because in the books you can see that the Wolf-Rayet phase is 10% of the lifetime of the lifetime of an all-type star, and this number is telling you exactly that. Yeah. So to take home for this object, we found 4,000 Wolf-Rayet stars in the antenna with MUSE. Half of the stars are nitrogen rich, and half of the other of the stars are carbon type. The ratio is 1, consistent with single stellar populations. And with this work, this is we increase the sample of extragalactic Wolf-Rayet stars to expect in the future supernova candidates and other byproducts. There are many other studies like Bridgman and others where they found populations of thousands of Wolf-Rayet stars, but this is one of the nearby systems. And I would also like to say a bit about this our last work in AM 0644741. So we also conducted a search for massive and Wolf-Rayet stars in this galaxy. As you can see, it has a ring. Actually, it's a double ring. You can see here one ring and here the other ring. So these systems are because of the interaction with the compact object who went through the disk perpendicular to the spiral galaxy, and it created like density waves, and that's why you see the star formation in the ring. So this is an HSP image, and a fourth color is from MUSE, from H alpha. So the star formation is tracing the ring. Yeah. So in order to look for the Wolf-Rayet stars, first we needed a catalog of the sources, that we didn't have. So we follow a semi-automatic approach. We use Sextractor to do first the catalog, and then based on the H alpha emission of of this channel or in MUSE, we found 185 regions which each have emission. After doing a careful inspection by eye of each of the spectra, we found like 4 of those objects were spurious. Some of them were AGNs, not H2 regions. So we ended up with 179 H2 regions. So all these H2 regions in reddish colors, they have a counterpart in HST, associated with star clusters in the optical. So this is the largest sample of H2 regions analyzed so far in this galaxy. There are also 9 X-ray sources, tracing the ring, excluding the center of the galaxy, and this is an AGN. We have 7 X-ray sources with luminosities higher than 10 to the 39 X per second. So these are ULX. It's very interesting. I will talk about these objects later. So this is the spectrum of one of these regions. We found the blue bone, again, very weak. If you are not looking for it, you might miss it. So this is a zoom of this line. It's very, very, very weak. However, if you measure the widths of the emission lines are narrow, are the resolution of the spectra, 3 angstroms, but the width of these lines is 12 angstroms. So it's a broad line. So it's because of Wolf-Rayet stars. And you see it very weak. However, it has a luminosity of 400 Wolf-Rayet stars. 400 Wolf-Rayet stars. And we also did the exercise of quantifying with H beta the ionization, like how many O-type stars would we need to ionize this H beta with this intensity. And we found 6,000 O-type stars. So the ratio between Wolf-Rayets and O-type stars is 0.1. Again, as the antenna. So 10% of the lifetime of O-type stars are in the Wolf-Rayet phase. We also look for nebular helium-2, as Carolina and Pepeviches do, but we didn't find, sadly. But this is not a low metallicity. What else? Okay, so we did after all this process, we did the measurement of all the lines that we see in the spectra of or in the 180 objects here. Here you can see that this is the extinction for each of the objects. So the higher the flux of in H beta, the higher the extinction. So we corrected the sample, not by the mean of the extinction, but each one by its own extinction. And now that we have all the lines, and we already found the Wolf-Rayet stars that we were looking for, with all this information, we can also do other kind of studies, right? Like determining the chemical abundances and the ionization states of these regions. So this is what we did. So in order to do the kind of studies that people do, like to look for a gradient in chemical gradient. Yes. It's kind of difficult to do it here because it's a ring type galaxy, right? So actually the disk of the galaxy is transparent. Actually you can see here some galaxies through the disk. Only the star formation is only in this ring. Actually, some people in our groups think that it's actually not a double ring, but only like a spiral arm, big spiral arm. So we define these rings based on in the isocontours in this filter. And between rings 6 and 12, we determined the oxygen abundances, and these are our objects. We didn't find a gradient. We also did the exercise with maybe azimuthal gradient. It's azimuthal. Yeah, and also we didn't find indication of gradient. The Wolf-Rayet cluster is here in red. It's above the median, but it's in the dispersion point. So we didn't find evidence of nitrogen enrichment it's not conclusive for this galaxy. So we did this with the strong line method, but we for this region, for the Wolf-Rayet cluster, we also have the necessary lines to measure the abundances with the direct method. So here we plot the nitrogen. We compared with other objects in the literature. We also did this work in the Cartwheel. And this is the iron. Yep. Okay, so now the ULX. So as I mentioned, we also have 7 ULX tracing the ring in this galaxy. And okay, so ULX are defined as point X sources. Sorry for here's the errata. With the luminosities higher than 10 to the 39 ergs per second. Yeah, so this number exceeds the Eddington luminosity. Yeah, in order to be a balance between the radiation going outwards and the gravity. And 3 of these ULX have a counterpart in optical. Yeah, but the rest they don't. So it's kind of a mystery why. So we wanted to check the ionization state of the 180 H2 regions and compare with the ionization state of the Wolf-Rayet cluster and with the ionization states of these 3 regions with ULX to see if there is something different, right? Like maybe some of them are because of shocks, I don't know. So we use these diagnostic diagrams. So in this case, this is oxygen 3 over H beta versus equivalent width of H beta. Here, our objects are here. These 3 symbols are the sources with ULX emission, and these are models for single and binary channel from Charlotte and Brusoil, which is in preparation, that paper, and different colors to indicate different ages. So, okay, it's very complex here, but I wanted to say that they are in our objects are in the low stage of ionization. It's not high compared with other systems like in the antenna, between log Q 10 to the minus 3, 10 to the minus 3.5. And then Cartwheel is higher. And they are consistent with the binary population here. And the edges are between, here is like 10 to 100 megayears. So the clusters ionizing this nebula are those edges. So we also use BPT diagrams, oxygen 3 over H beta versus nitrogen 2 versus sulfur and versus oxygen 1. Yeah. So our objects are here. So the objects with ULX emission and Wolf-Rayets, they are not in different regions of the BPT diagrams. Actually, the ionization is because of the star formation. And we also found they are consistent with ionization by clusters, young clusters. Yeah. And also to take home about this object, we conducted a search for massive stars and Wolf-Rayet stars also in this double ring post-collisional galaxy. We found a Wolf-Rayet population at 400 Wolf-Rayet stars in only one of the 180 clusters. At first, we expected to find as much Wolf-Rayet as in the antenna, but the antenna is in the process of collision, yes, and this is in a post-collisional process. And also the ratio between Wolf-Rayet stars and O-type stars is 0.1, indicating that 10% of the lifetime of the O-type stars here are in the Wolf-Rayet phase. We also study the chemical abundances and the ionization states of these regions. We didn't find indication of radial or azimuthal gradients. And we find that the H2 regions are consistent with photoionization by star clusters of ages 3 and 20 to 15 megayears. And in BPT diagrams, a binary population is needed to reproduce the observation. This is all I wanted to show you for today. Right now in Potsdam, I'm studying local systems like in the LMC, this N11. In the LMC, in the very center is a Wolf-Rayet star, and here is a cluster of O-type stars. So I'm studying with models of power. We are determining the stellar and wind parameters of each single star. So in order to have the ionization, mass loss, ionization, ionizing photons, exactly, of each of the stars in detail. So this will help to be more precise in extragalactic studies. Yeah. So thank you very much.
Well, thank you, Mauricio, for the very interesting talk. So now, questions for Mauricio? Okay.
Thank you very much. Very nice talk. You've just said before this view graph that the ages you were talking about were between, if I wrote it correctly, 10 and 100 million years from the plot, from the previous plot to that, from that plot. But then you say that from BPT it's much younger, right?
Okay, yeah. So so half of the objects here are in this range of colors. Yeah. Yellow, let's say 1 to 20 million years. The other half, it was a mistake by my side. Yeah, they are between ages between 20 and 100 mega years in this diagram. And in these diagrams, yeah, they're also like in this range of ages between in the yellow and red models.
Okay.
So
it's consistent.
Yeah, they are consistent.
But the other thing I've seen is that for this ring galaxy, you get the stars have to be mainly in binaries.
Yes.
Whereas for the antenna, you said that it was mainly in single stars, right?
Yes. So
what do you think is producing that difference?
So one thing could be like the metallicity, but for example, the antenna is above solar, and this one is more like LMC, like metallicity. We don't know if this is the factor, yeah, but at less metallicity, you expect that the stars have less winds, so the channels to produce Wolf-Rayet stars are binary. So maybe is the direction of the explanation. Yeah.
Another question?
Thank you, Mauricio, for the talk. It was very interesting. And I wonder whether, I mean, the idea of the say interacting galaxies, or was it a bit to trying to, I mean, the original idea, was it to trying to test or to check the Wolf-Rayet production in environments strongly affected by the condition for star formation, like the interacting galaxies? So is it different from the average, in your opinion, the other nearby galaxies, or even from our galaxy? Did you find that this the terrific history they have for these galaxies with interaction affected the statistics? Okay, so the main idea was to look like these massive and Wolf-Rayet stars in these interacting galaxies because of the interaction, the
the trigger of star formation is in galactic scales. So you can see like recent star formation in galactic scale to increase the sample of massive star, like recent star formation. Of course, there are other galaxies with high star formation, yeah. Like, but in interacting galaxies, is almost like it's guaranteed that you will have like massive stars. Like, for example, the Antennae is a very impressive example. And we wanted, okay, now we have analyzed these three systems, also Cartwheel and NGC 15. Well,
69.
Yeah, that one. Yeah, and so we wanted to see like if there is a difference, previous to the collision, during the collision, and post-collisional galaxies. Yeah. So at this point, we'll have three examples, but the main reason to look in these interacting galaxies is just because of the star formation in galactic scale. So to increase the sample and to increase like the number of progenitor candidates to explode like supernova 1BC.
So the largest scale star formation in the whole galaxy.
Yeah,
it was to have to test whether that affects the overall population.
Yes, and we would like to go. So these are very metallic, right? The lowest metallicity that we have is LMC, right? Yeah. So we would like to do the kind of studies that you do like in low metallicities. But we will need
it is interesting as you mentioned before in the context scenario, whether the channels, you can change the channel to the W or not.
Exactly.
So I think this is a very relevant test. And I have a curiosity also, because you have derived the iron abundance. So did you use the 46? Did you use the artificial? So is it difficult in this spectra? Because it is very difficult normally.
Yes, it is.
But, how do you find that in this kind of galaxies?
Yeah, so maybe we can discuss about details like in the paper. But we, for example, look at this. We have this. Okay, but we have the equations in the paper. I can show you later.
Oh no, it's just that.
But it wasn't easy. Actually,
it was easy to measure the iron 3 line in this kind of galaxy. It was relatively easy.
Because for the Antennae was more easy.
It's in the mass.
Yeah, but this is the iron 3 here. Yeah, actually in this case it's stronger than helium-2. In all the bonds we found.
Okay, so there.
It's there but in this galaxy, the last word is not so easy. It's very weak.
Okay.
Actually, it's not. Actually, this is the limit of like the observation with. Yes.
Yeah, I have a couple of ones. I don't think it's really a question, it's just curiosity. You mentioned that you find a couple of multiple Wolf-Rayet systems in the Large Magellanic Cloud. Do you know which method or which type of binaries are these? Because I'm just surprised that being that far away, you can resolve them nicely with a spectral.
In the LMC?
Yeah.
Yes. So in the LMC, actually have another talk, but maybe for other time, right? So we have. Okay, no, I cannot show you. So we have a spectra in the UV from Hubble and in the optical from X-Shooter. And we also, so we are analyzing the physical parameters with this spectrum, right? Temperature, surface gravities, chemical abundances, terminal velocities, everything that you can measure in this spectra. But the binarity is checked with other observations with giraffe, and these are multi-epoch observations. So these are in periods of hours, days, months, and that's it. So we can check if there is like a binarity features. And binarity features, they mean, so you have two kind of binaries, SV1, SV2. So for SV1s, we check a radial variation of the line between two epochs of observation. It's not that you see like absorption lines, right? So you see only the radial difference. This is evidence of SV1 binaries. And SV2, you see this, but also a difference in the profile of the line, right? We check, for example, in the helium lines. Sometimes, if you are lucky, I have an example here. This Wolf-Rayet was thought to be a binary because in the bombs that I show you, the blue bomb and the red bomb, above the bomb they have absorption lines of, let's say, of the same element but in absorption, indicating another component, cooler, O-type star, but with more shorter apertures from FOSS, also in the HST, 0.3 arc seconds. We resolved a system, and actually it's not a binary. It was just another object there. So in order to see binarity, you need to see the difference in velocities in the lines. If you see in only one spectrum features of two stars, it's not indication of binary. It's indication of component spectrum. Yeah, they can be like projected, but not necessarily gravitationally linked. You will need to see the velocity. And at the distance dependency, it's possible. It's still possible. It's not possible in MUSE, in Antennae, because there you not see, you cannot see individual Wolf-Rayet stars. Yeah.
Also,
Here's another question, then Martin.
When you show the lines, the thick lines that are indication of Wolf-Rayet presence in the extragalactic antenna, for example. I'm talking from absolute ignorance here, but could it be possible that the winds present in the intercluster medium, the inner winds that are supposed to be these supermassive star clusters, affect or enhance in any way the emission that you detect with this rather small line? Or
like so the broadening of these lines that we have observed, like individual Wolf-Rayet stars, we know that they're weak because of the strong stellar winds. So this is in the optical. We also have indication like in UV for individual Wolf-Rayet stars. Maybe later I can show you like these features, but this is because of the winds are like the velocities there are 10 to the 3 kilometers per second. So this is why they're broad.
okay,
Yes.
this,
And these other phenomena is interesting, but I don't know what is the effect.
I mean, the width is kind of clear because I also work with some Wolf-Rayet.
Okay.
The intensity of the line
The intensity?
could have a component that comes from the interaction of the winds. That is also obviously an indication of Wolf-Rayet presence. But
Okay. I see.
I'm not sure. I don't even know if that makes sense.
Okay.
Because they are all expected to be like most of them in binary higher order multiple systems.
So, for example, in M81, where it's a 3.6 megaparsec, it's far away for local people, of course. But it's still far to look for individual stars, 3.6 megaparsec, right? So, this galaxy, we have two objects which are multiple. Yeah, but the dominant star is a WC type. Yeah, so that's why they are in this region, WCs. But we don't know if they are binaries because, of course, because of the bomb. Okay, it has the intensity of 2 or 3 Wolf-Rayet stars, but we don't know if they are like binaries, like gravitational. But yes, the intensity of the bombs can tell you the number of stars contributing to these features.
And one last thing I promise. And you showed before a plot of the ratio of carbon and nitrogen Wolf-Rayet versus metallicity.
Yes.
And I'm just curious, where did you get that one? Because it can be very handy for my own work. And two models with single and binary evolution.
Yeah. Yes. So there are several groups competing, but I would recommend BPAS from the group of J.J. Eldridge in Upland. So he has models for single and binaries. Many other people only have for single, right? But if you want to study like the young stars, so we know now in papers by Sana and others that around at least 70% of the massive stars are in binaries. Yeah. Yes, so you have to check for the binary channel also when you study massive stars. Yeah. But we think that binaries are more important than low metallicities. Yeah.
Okay, Martin.
Okay. Thank you very much for the talk. In this last object AM0644, you mentioned that there are several ULX.
Yes.
It seems to me to understand that they don't have a strong impact on their surroundings.
No, at least in the PPT diagrams, in the diagnostic diagrams, we didn't know that they were ULX. Okay, so we have 9 X-ray sources. One is a center, which is not ULX. This is a quasar, and these are ULX because they have these luminosities higher than Eddington. And 3, for example, this one, I think this one and this one are associated with a cluster from Hubble. You can see the cluster. For example, here you cannot see anything. You cannot see the cluster, but it's still in the ring. Yeah. Also, I think here and here, yes. So they don't seem to have an impact in the ionization state of the optical lines that we measure. Maybe in other.
But maybe they're passing through dust regions, right?
So sorry.
Maybe they're with over regions where dust is important, so you cannot see the optical, but you see that in the X-rays.
Okay. Yeah. So it would be interesting to check that. I have.
What's the typical absorption?
So the absorption. Okay, these are the extinctions for the ULX sources. Okay. So we also corrected for the probable, maybe most likely underlying stellar population, because of when you see like at these distances, almost 100 megaparsec, you see like star forming regions, and you have like stars of not only young ages but also very old. And so we use with Brusual and Charlotte, we model the older stellar population, because in H beta the older stars can have absorption, so they can dilute the emission of H beta that you are measuring. So we measure the fluxes after the correction of the underlying stellar population.
That you can have such high extinction that you see nothing in the optical. So you can correct or whatever because you don't see it.
So the extinction, we use the ratio between H alpha and H beta for the H2 regions, and so we corrected before, like for the it's a small absorption that you observe here. So it dilutes the H beta, but it's not like not a big effect.
At any rate, it seems that there is these don't have any effect on their environment. That is somehow surprising to me. I know it's probably based on the mechanical and ionizing feedback of ULX in their environment, and there are evidence of regions, hidden plus regions associated apparently with those. So in this particular case, there is no.
Actually, this one is the most interesting object because it's a star forming region. It's also Wolf-Rayet cluster, and it's also ULX. This. But in the BPT diagrams, you see them like in the region of ionization by star formation. Like in the optical lines, maybe if you go to the other lines.
No, the comment is that this question about I think is very relevant in relation to the helium-2, for instance, ionization that has been, claimed many times. Even for that, we have some paper together with that. That are the ULX responsible helium-2 ionization.
Yeah. So,
and then you have found 7 of them where you don't find any relation.
But we have also.
So this is very interesting, at least as a counterexample to use for reference.
So for example, we also did this with the Bacara. So the Bacara lead the other galaxy in Cartwheel. So we did like several papers in Cartwheel. One of those we found helium-2 nebula, narrow.
It has been found many times.
It also has a large population of ULX, but we don't see like a clear contundent evidence.
So that's the point. So the point is not a straight relation.
No.
Yes.
No.
One to one.
I have another galaxy that we can discuss maybe later. This is also a ring type galaxy with around 10 ULX, and we can look for the Wolf-Rayet population and relate them.
I have one question. So I think you mentioned that in the collisional galaxy that you expect hundreds of Wolf-Rayet stars, right? And at the same time you detect the Wolf-Rayet bump in only one region, right? So if I'm not wrong. So how do you explain this lack of detection? Because I mean, one would expect more detections of Wolf-Rayet bumps, right? If you have hundreds of Wolf-Rayet stars. I'm asking because at the metallicity of this galaxy, you don't expect a very low Wolf-Rayet line luminosities that can justify the lack of detection. So do you understand what I mean?
Yes. So this is why I like to compare with Antennae always, because for example, with Antennae is like in the process of merging. So you have like very young star formation. Like actually, that's why I mentioned the equivalent widths of H beta, like higher than 50 angstroms, like 4 megayears. And in this case, in the BPT diagrams, we found like these are ionized clusters of 20 or older stars. And remember that the Wolf-Rayet in the single scenario are as young as 2 to 4 megayears, and in the binary channel as old as 20 megayears. So this is in a post-collisional stage. Antennae is in a pre-collisional or in the process of collision. So maybe this is why we don't see any like Wolf-Rayet stars, or only here. And it's not that you expect like hundreds. It's like this bump is consistent with red. Yeah. And what else?
They are gone.
Yeah, I think they are gone. I think it's related with that. With the age of the clusters. They are not as young as 4 megayears.
Okay.
Maybe.
I just want to comment. Why do you call the antenna pre-colliding? Because
sorry. Maybe it's in the process of collision, right? So it's like a picture, like it's in the process of collision. Like this is one galaxy, this is the other one. Actually, in the bridge between the two, we found like how many Wolf-Rayet stars? Hundreds here. It's in the process of collision.
And in the same vein, the ring galaxies are not.
This is a post-collision. Actually, we don't know for example, here you see the two galaxies, but in the ring type galaxies, actually, we don't know which one was the collider. It has to be a compact object because of the simulation, like when people doing that. Like has to be compact object, like going perpendicular to this and creates this way. But and there are like 3 candidates here, but we don't have a spectra. Like actually, would be nice for a proposal to look for the cats for the galaxy that yeah. But we don't know the collision.
Okay, so if there is any question further, so so then let's thank Mauricio once again. Thank you.
Thank you.